Okay, now we've got the antiderivatives of e to the x, and just like with the trig functions in the previous video, what happens if the inside of the exponential function is just some generic linear expression kx plus b? Well, we know that the derivative of e to the x is itself, so the antiderivative of e to the x should also be itself and remain unchanged. However, if the inside of our exponential function is something more complicated than just a single x by itself, but rather something slightly less, something slightly more complicated, such as the linear function kx plus b, then we, much like with the trig functions, have to compensate for that chain rule. So instead of multiplying by the derivative of the inside for the chain rule, when we go backwards, we're going to divide by the derivative of the inside. So we have this leading 1 over k. So here, this would be a half e to the 2x plus c. Here, we'd have just e to the x plus 1 plus c, because the derivative of this is just 1, so you don't even notice that division by 1. Now here we got to be careful, because, and I would like to just emphasize with an additional set of parentheses around that. I should have typed that. Here, we have e and ln being inverse functions. This is really just the antiderivative of 2 times x minus 1 dx, which is, we can factor the 2 out, and then we're really just going to be taking the antiderivative of this, which is a half x squared minus x plus c. Now some of you might be wondering, shouldn't the plus c go on the inside here? Shouldn't it be something more like this? And sure, you're right. But here's the thing. If we go ahead and distribute this 2 through to everything, do you see how this becomes plus 2c? And isn't, if c is just any real number, isn't 2 times c also just some real number? So whether or not you choose to do that or not, it doesn't matter mathematically. And for simplicity, we choose not to do it like that. So it's always, you find your antiderivative, one antiderivative, and then just add c to it. Now here, e to the 3 is a constant. It's not, there's no x's in it. So the antiderivative of this is just e to the 3, so e cubed times x plus c. All right, for example 6, what we'll have here is we are given the third derivative and we're asked to find the original function. And we're also given some additional information that will help us along the way. So ultimately, f of x should be equal to the integral of the integral of the integral of f triple prime. Right? Because this first layer here will give us f double prime of x. And then if we integrate that whole thing, that will give us f prime of x. And then if we integrate that whole thing, we should be left with f of x. We're not gonna do it all out like this because it'll get a little bit crazy, but that is ultimately what is true. So what we're gonna do here is we're gonna work in stages. So first we'll start with the fact that f double prime of x is equal to the antiderivative of f triple prime of x. And by x, I do mean t, because t is our variable here. So we'll just make that quick little replacement. So this is f double prime of t is the antiderivative of f triple prime of t dt. So we can replace in what that is. F triple prime of t is e to the t. We'll find our antiderivative, which is just e to the t plus c. And now, since we're going to be doing a couple successive anti-differentiations, it'll be useful for us to number our c's. We'll have c1 from the first round of integration, c sub 2 from the second round, and then c sub 3 from the third and final round of integration. You don't have to use c's. You could use capital A plus B plus C, and I guess you don't even have to use capital A plus B plus C. You could use lowercase, or you could use kitty cat face. Whatever you want to do. So, that's an expression for f double prime of t. But what do we know about f double prime of t? We're told that when you plug in t equals 0 into the second derivative, you should get 2. So, 2 should be equal to e to the 0 plus c1. E to the 0 is 1. So this should mean that c1 is 1. Which then means that f double prime of t, if we replace this c1 information back into the original second derivative, this would be e to the t plus 1. So now that we have that, we can just rinse and repeat that entire process. We know that the first derivative, f prime of t, is the antiderivative of f double prime of t dt, which is the antiderivative of e to the t plus 1 dt, which is e to the t plus our second constant of integration, c2. Likewise, we're told that when you plug in t equals 0 into the first derivative, the result is 1. So 1 is equal to e to the 0 plus c2, which gives us c2 equals 0, which gives us f prime of t, the first derivative, is e to the t plus t. And yet again, rinse and repeat. So, the original function, f of t, is the antiderivative of the first derivative. So this is the antiderivative of e to the t plus t dt, which is e to the t plus a half t squared plus c3. And again, we're told that when t is 0, f of 0 is 3. So 3 equals e to the 0 plus c3, which means that c2 is equal to 2, and therefore f of t is equal to e to the t plus a half t squared plus 2.